Great. So, hi everyone, and welcome to this seminar. So it's a great pleasure to have Ben with us today. He will present asymptotic properties of the gauge and power of step indicator saturation. Ben, you have 1 hour, and we may interrupt with a question if that's fine with you. So I should also announce that this is recorded, so you can either ask your question, post the question in the chat, or if you prefer, I can unmute you and you can ask the question directly. So the floor is yours, Ben.
Thank you very much.
Thank you.
And I'm certainly open to questions on the way. And let me start by thanking you for inviting me to this virtual time series seminar. So it's going to be exciting. It's written, the paper is written together with Matthias Kern, who is at ESTM in Berlin. The title of our paper is Asymptotic Properties of the Gauge and Power of Step Indicator Saturation. So I'll start the talk by explaining what the step indicator saturation is, and then I'll also tell you what the gauge is, because that may be both of those concepts you may not be familiar with. I should say the paper is circulated as a discussion paper from Nuffield College, and you can find a link from my website, and there's my website is here, but I guess you can use Google these days. Okay, so let me get started with the outline. So step indicator saturation, that is an algorithm for detecting level shifts in time series. And it was suggested in a paper by Jenny Castle, who is here, and Jürgen Dornig, and David Hendry, who's also here, and Felix Prettis, and this is a 2015 paper. It's an algorithm that's implemented in Oxmetrics, in R, and in eViews. And in the original paper, there's various analysis of this algorithm. And we go a bit further in this paper by giving a bit more asymptotic theory. And so what I'm planning to do here is to first tell you about what is step indicator saturation, or SIS, as we call it. Then I'll give you an empirical illustration to give you a feel for how it works in practice. And then I'll go into this issue of what is a gauge. So it's about controlling the type 1 error. And I will discuss how we want to control that error, and then afterwards give some asymptotic properties. Then we go into power, and that's of course about controlling type 2 errors, where we want to think about the power about this algorithm, but also about other algorithms. And then I'll come back to the empirical illustration. Hopefully the theory will then help you to understand the empirical illustration. So the first thing is, what is SIS? What is step indicator saturation? And the basic model we have in mind is a time series regression model, where you want to regress yi on a vector of time series xi. And then what we think is that there could be level shifts anywhere in the data set, and there could be several of these. We don't know how many there are. So let's just put a level shift for each possible observation in the data set. So these level shifts are, in this talk, they're made so that this indicator is 1 up to a certain time j, and then it's 0. You could, of course, also choose it the other way, but this is how we've done it. It's equivalent. And so we have our n observations, and we want to estimate this. And then, of course, we cannot estimate that by regression, because we have more regressors than observations. So there'll be an issue about how do we estimate this thing. And basically what we want to achieve by this is to determine how many of these delta j's are different from 0, and we want to know their location. So there are a couple of special cases, one could say, that have been discussed in the literature. There's actually quite a lot of literature about finding structural breaks. And the ones I will focus on here is basically what we know as the Andrews test. So in the Andrews test, we think of at most one central step shift. And it's basically the likelihood ratio method. There's a likelihood ratio test that gives you a test for whether we have a break somewhere in the middle. The method doesn't work so well for finding breaks that are in the endpoint, so we trim the endpoint. Buy and Perron has a generalization where they allow up to m distance shifts, so we need trimming at the endpoint, but also trimming between the different breakpoints. But we see that as a kind of generalization of the Andrews test, so we actually don't theorize about Buy and Perron. One could also focus on what happens in the extreme periods, in the start of the sample and the end of the sample, and then you could use something like the method developed by Yao Davis and Hidalgo and Seo as another paper about this, where you use some other methods to find out what happens in the extreme parts of the sample. What we have in mind here is that we don't want to set an upper bound for the number of breaks. So it's in that sense an unbounded number of shifts. Of course, it's bounded by n, but we don't have any other bound to it. And then we also want to allow shifts that are close to each other. So we don't want the trimming. So that can be relevant when you want to do forecasting, because you may have a break right in the end of the sample, and that's very important to discover and deal with when you forecast. And you could also, as we will see in the empirical example, have some shifts that happen very close together, and that we would like to be able to deal with. So there are some differences in assumptions in these methods. So the non-cis methods basically allow you to have errors that are not necessarily normal. They should be IID or approximately IID, but they do require that the regressors are stationary. Here it's the other way around. We need the errors to be normal, but we can have regressors that are non-stationary. And so the basic idea is that overall in the regression, you may have some errors that don't look normal, but we kind of sort it into the step shifts that captures the non-normality, and the rest is uninformative. On average, it looks good, it's normal. So that's the idea. Okay, so what does cis do as an algorithm? Well, let's first think about the ideal solution you could have to this. You could fix a number of step shifts. And if the number of step shifts is smaller than the number of observations, you can then use regression. So you could make a subset of size m of step shifts, and then you can have these step shifts in m different locations across your sample. And then you can estimate by regression. And then we search over all choose m out of n possibilities for locating your step shifts. And then on top of that, we need to search over the number of step shifts. So we search over that m as well. And that's computationally infeasible if you have more than about 20 observations. And so what we have to do in practice is to approximate this problem computationally. And there's a related problem that I've worked on quite a bit. It's a situation where we have impulses instead of steps, and that gives us what is called impulse indicator saturation, which was suggested by David and co-authors about 2008. So that's the same thing. Instead of step shift, we have impulse shifts. If you choose a particular number of impulse shifts, then it's similar to what is called the least trim squares estimator, which is used in robust statistics. And we have been working together with Sonja Hansen first, and then later with Vanessa Benguerico. We have worked on both of these algorithms. And we have some papers that are published, and theory is in progress on this. But now we want to look at cis. And so we have the step shifts, and we need to solve that computational problem in the sense we want an approximate solution that is good in some way. And the state of the art, I guess, is the autometrics algorithm that Jürgen Dornig developed, and which builds on the PCGET algorithm that Hendry and Krolsik developed, which again built on the multipath search idea of Hoover and Perez. So the idea is that you look at blocks of regressors. We can't have all n step shift. We take a block, And for each block, we can then use a multipath search to look at a lot of different combinations. And then we can look at different blocks and combine everything. And that allows us to sort of get around in all the many models we would look at in the ideal solution, but we don't look at all, but we, in some clever way, we want to look at the most important ones. So there's no theory for what are the important ones and how good it is, but you can try with simulation and see what is it good at, this particular algorithm. And so what we are going to do is we are going to consider a stylized version of this and theorize about that. So we call that stylized SIS. So the idea is that we have two blocks. We have a first block, which is, you could think of as a first half of observations up to N1. There we have a model where we have a regressor, we have an intercept for these observations. And then for all observations after N1, we stick in a step shift. And so what we get out of that is that we get this following algorithm. First, we choose a cutoff value C. And then we calculate the least squares estimators from this regression. And you can do that in two equivalent ways. One is to estimate the whole model on the full N observations, or you can estimate it on the N1 estimation, first observations. So you don't worry about the step shift initially. So we get these estimators for beta and sigma hat, and I guess also delta N1. And then we can, if you then implement that in the full model, we can compute t-statistics for these delta J's. And then there's a little fiddly thing here. You can see the breaks, they go from N1 plus 1 up to N. But the last delta N is of a different nature than the other deltas. So in our theory, we just forget about the last one. Asymptotically, it doesn't matter for what we're doing. So we focus on what we call the set I20, which is the second block apart from the last observation. And then the idea is in the fourth step is for each j in this set I0, 2, we declare that we have a location shift if the t-statistic is bigger than our cutoff. And then that gives a question, how do we choose the C? And then the idea is we want to look at the type 1 error and then choose the C from there. And in particular, we will look at what we call the gauge. Once we have done that, we also want to look at the power to detect shifts. If we have two algorithms, for instance, the Andrews test and this test, we can now calibrate them so that they have the same type 1 error, and then we can look at the power and then say which is better in this situation. Okay, so let me now go into the empirical illustration. So what I have here is UK labor productivity per hour from 1980 until 2021. And you can see here until about 2008, it's more or less linear. It is a slight curvature. It gets a bit slower over time. The growth gets a bit slower on time. Then we have the financial crisis. And then after the financial crisis, we have a very different slope than we had before. And then in the very end of the sample, we get to the COVID pandemic where weird things happened. Here on the right, I have the changes in the log output. And you can kind of see that there's a kind of a level shift. The first observation seems to have a different level than the last observations. It's not a very big shift, but economically it's of course very important. And the politicians in the UK are very worried about this lack of growth in the labor productivity. And so, for instance, we got the Truss government for 40 days that was trying to do something desperate about this, but all the politicians worry about this. And so let's try to model this. So the first model I have is a model where we forget about COVID just to make things easy. So we end in 2019, regress today's values on the lag values, and we get this model here. We have a residual standard error, we have 160 observations, we have misspecification tests, we use a 1% level. We could look at a normality test, that looks fine. We could look at tests for autoregression in the residuals, it looks fine. We could look at Chow one-step test that's David Hendry has always been very concerned about looking at recursive graphics. This one I use here is a joint test developed with Andrew Whitby, where we find the maximum is achieved in 2008-3, the financial crisis, but it doesn't reject. It's not bad enough to give a rejection. We also apply the Andrews test. It has the worst point in 2004, and it's sort of marginal decision whether you want to reject or not. So the Andrews test seems to point at not something that's necessarily economically meaningful, whereas the Chow test points at something that is meaningful, but without being significant. Now, so how do we want to do this? So now we want to go all the way up to the most recent data, so we include COVID. And so what we do is we apply this stylized CIS. So we saturate with step shifts in the 2000s, after 99, fourth quarter. We have the same model as before, regress today's difference on yesterday's difference with an intercept, and then we have all the dummies here, and you can see it's swapped around here. Then we have all these many dummies, and then what we then do is we keep shifts with t bigger than the 1% critical value in the normal distribution. We haven't explained why we do that, but that's what we do. And then we keep those, run the regression again, and then we get these dummies here. We keep them from the first decision, and now we look at these. And you can see there's, in 2000, there's something up happening, down happening in short succession. In 2008, we have a dip down and a barely significant value for this dip down. Then with the pandemic, we have 3 big shocks in succession. So that's the empirical model. So now let's look at the data again. Here I have in the top the log output as before and the differences as before. In panel C here, we have this one step ahead Chow test that's like you would find in our metrics. This is now the pointwise critical value. So the pointwise critical value gives a rejection in 2008-3, but the joint test doesn't. And these are now the fitted models. So the red curve is the fitted AR1. So remember, this is the data, and the axis here goes from minus 0.25 to plus 0.25, and here the fitted value is somewhere in the middle. And we have something very dramatic happening here with the COVID, where it's actually truncated. This goes all the way up to 8% and all the way down to minus 4%, but I've truncated it to be able to focus on what happens. And then we have the fitted model by stylized CIS, gives you this level, some up-down thing, and then a slightly different level, which is there's a slight slowdown after 2000. Then 2008, we slow down again, nearly to 0 growth, and then we have some up and down things happening, and then very short period to find out what happens afterward. So that's the fitted model. And that sort of, this fitted model here fits much better with our sort of perception of these data, I think, the blue line. And the slowdown in the economy, we see that that's what the politicians are worried about. Okay, so now let's think about this algorithm. How do we measure type 1 error? And so what I've done here, I've just written down the model equation again. I have written the algorithm, and then we have this question, how do we choose the C? And choosing a C, it's a multiple decision problem. We have to decide about all these many deltas. Which of them do we want to keep? So the gauge, it's we want to use it to calibrate this cutoff C from the type 1 error. So if we just think back to classical test theory, there we make one decision. So we may have a t-test. We have a t-statistic. It's t-distributed. We find a critical value. So the probability of rejection is equal to alpha, our usual 5%. We can also write that as the expectation of the indicator for having a big t-statistic. Now, if we want to do multiple decisions, then there are many ways you can generalize this idea. And the one we'll focus on is what we call gauge. The name gauge comes from, I think, from this paper by David Henry. And it stems back from how Hoover and Perez analyzed these ideas originally. There's a big literature of multiple decision problems. There's a book by Miller from 81 where he calls it the expected error rate. There's another more recent book by Dudois and van der Laan where they call it per comparison error rate. So it's a concept that is known under different names. So what we have here, and so what we at least can say, gauge is more catchy than the other ones. So I'll keep the gauge name. And so we can measure gauge in two ways. So the basic thing we do is we look for each of the many decisions in our set I2. This is the second sample, subsample. We look at the t-statistics and declare a step shift if the t-statistics is bigger than c. We can then take the expectation of that and add it up, and then take an average. And that we could call the frequency gauge, the frequency gauge. And the N2 here is just the number of observations in this I20 set. But we can also just look at the count where we don't divide by n. And that the count I call capital gamma, and the average we call lowercase gamma. So why do we want to do this and not something else? Well, an important feature of this gauge is that it is additive. So that means that when we do our asymptotic analysis, we get some simplifications coming out of this. And so we can essentially analyze events one by one, or you could think of this, it's a bit like an empirical distribution function. So we can understand it in that way. So we can use techniques from empirical processes to analyze it, or some other techniques, depending on exactly how we want to analyze it. So that's very useful. And it's also, in practice, it's useful if you feel that you can tolerate some false detections as long as you get the deviations from the model. And an obvious alternative is what is called the probability error rate or the family error rate, where you say we want to have no false rejections at all. So here we look at, this is the complement, so you have at least one false rejection, and then we can find the probability of this set. And in order to analyze this, then you need to understand these indicator functions jointly. And so that's a harder problem to analyze. So that requires simultaneous analysis of these events. But perhaps if you have a feeling that with your data set, you don't want any false detections at all, then perhaps this is what you would want to control. But in a sense, the main purpose of this is, well, there are two purposes. One is you need to choose a cutoff. You can choose it from either of those two, but then you can choose a gauge, target gauge that is larger or smaller. So you can kind of implicitly adjust for this if you want. And then the second purpose is to say, if you have two different algorithms, which one is better at picking up this particular type of alternative? By taking the two algorithms and making sure they have the same gauge. Okay, so now what we want to do is to go in and say, can we find the gauge of our algorithm? Before I do that, I should tell you a little bit about the estimators of the deltas. So remember in this stylized sys, we have put in indicators with steps for each of the observations in the second half. And then we can do a reparametrization where we put an indicator on the X down here. We have an indicator for the level in the first sample. And then we turn these step shifts into indicator for a point. And this is a very important consideration, which is in the original paper by Castle and Henry et al. And then one can work out that in this second equation, you can estimate the etas simply by the eta j, I guess should be the yj, not the yl, the yj. So because you have perfect fit in the second sample half. And then you can work out what's the relationship between the etas here and the deltas. And then you find out that the deltas are estimated by the forward difference of the y's minus beta hat times the forward difference in the x's, where forward differences are defined this way: today's value minus tomorrow's value. So all the analysis will be about these forward differences. So this is a kind of a residual that we want to understand. So now we can go in and rewrite the gauge. And we're interested in the forward differences. So let's first think about the errors. We assume they're IID normal. We take the forward differences. They will then be one dependent, because if you have two forward differences next to each other, they have one overlapping epsilon, so they will be dependent. But if you go two steps apart, you get independent. And the the variance of these forward differences is 2 times the original variance. And so we can rewrite the gauge. So that's the average of all these expectations. Well, I guess if I have a hat over here, I should actually not have an expectation here. So there's a little bit messy here. So I have to decide whether I have a hat or an expectation. I can't have both, but I hope you can live with that. So we go into these t-statistics. What I have in the numerator of the t-statistic is delta hat that we want to compare with 0, which is we found that was the forward difference of y minus beta hat forward difference of x. In the denominator, I have some kind of variance, and that involves a sigma. I have estimated it involves some kind of element in a hat matrix, and the c and the square root 2 coming from up here. And so I can then rewrite it further. I can use my model, write yj in terms of epsilon j and a beta. So I have here the forward difference of the epsilons, the estimation errors for the betas, and then the forward difference of the regressors, and then this stuff on the right-hand side. And then we can see if we don't have any estimation error, so beta hat is equal to beta, then this term here cancels. So we don't have any regressors appearing. If sigma hat is also equal to sigma, then it's also simpler on the right-hand side. And if we put these weights to 1, life is even simpler. And so if we then look at 1 minus this gamma, then we get the empirical distribution functions of the forward difference of the epsilons. And so these forward difference of the epsilons, they're now one dependent. So it's not a standard theory, but you can look up in Billingsley. He has a chapter about this. So we can find the asymptotic distribution in that case. So, okay, so now let's have the theory. So the theory here is boiled down to 3 pages. The appendix is unfortunately longer than 3 pages, but that's life. So I'll skip the appendix. So we need some regularity conditions that take a page to write down in the paper. Here it will be 2 lines. So we need a known error distribution with certain properties. And if it's a normal distribution, you're in business. Second, we need some regressors with certain properties, and they can be stationary, they can be non-stationary, but they cannot be explosive. And then we have this little remark that the first condition is stronger than Andrews, the second is weaker than Andrews. Okay, then we fix C so that the probability that the forward difference of the epsilons of these normal distributions is that's bigger than square root 2 sigma c, that's equal to gamma. So we can find c from gamma. Then if we then look at the empirical version of this gauge, then we can show that this is consistent. We can also show that if we more normalize by square root of number of observations here in the second sample, it doesn't matter because we need some kind of, we can actually play a bit around with that the second sample size could be nearly everything in n, but I'll not go into that. So you can just, for the purpose of today, just think about n2 as being half of the sample. So we apply this, and then on the right-hand side, we get a normal distribution, and it has an asymptotic variance that now will depend on the correlation structure between the forward difference of the epsilons and the forward difference of the x's. This is a bit messy, and I'll give you some comments about that. And so what we if we go back and say we have the consistency, so that tells us for a very wide range of regressors, the method gives you the right kind of target for your gauge. Then you can ask as a second order question, how precise is this? How does this precision depend on the type of regressors you choose? And that's all buried in this variance here. And it does depend a bit. It turns out that if you have completely exogenous regressors or you have random walk regressors, then it doesn't depend on the nature of regressors. But if you have stationary regressors that are sort of not strictly exogenous, but only exogenous relative to the error, then you get a correlation between the difference of the epsilons and the difference of the x's, and that goes in here. So we have tried to explore these formulas numerically, and that's in the paper, and we get some variation, but it's by the experiments we made, the change, the difference we see in the variance is about a factor of 2. So it's not a lot of variation we get across the experiments we looked at. So it's fairly stable. One get out of that exercise, we see it's fairly stable. Now, the next thing we could do is we could look at, instead of look at the relative gauge, the frequent gauge, we could look at the absolute gauge. And then we get into a Poisson theory where we say, instead of selecting a proportion of outliers or step shift, false detections of step shift you can tolerate, you give me a number. And so you give me a number, and regardless of n, I want that number. So I want to have my probability targeting the ratio of that number over n. And then what I get out of that is I must choose these CNs, the cutoffs, to drift to infinity. They will drift fairly slowly because we are on the tails of a normal distribution, but they will drift slowly to infinity. If we then at the same time say that N2 is a psi proportion of the whole sample, then we can show that the absolute gauge is asymptotically Poisson distributed with a parameter lambda, which comes from here, and then psi, which comes from here. In the paper, we also look at a method we call split half cis, where you first use stylized cis on the where you saturate the second half, and then you use stylized cis where you saturate the first half, and then you combine, and then you get two independent Poissons out in the limit, and then the two proportions add up to 1. So you get, for the gauge in that situation, a Poisson distribution that only depends on lambda. But that's sort of a minor detail. Okay, so I'll skip the proofs essentially, but give you a few more comments. So the first thing to bear in mind is that the errors, the differences of the errors are one dependent. So the residuals that we'll be interested in, they are approximately one dependent. So the fixed C results, they work as follows. If we have no estimation error, then we have an empirical distribution function of these one dependent errors. And then there is, in the third chapter of Billingsley's book, there's some theory we can use for dealing with that. And then the estimation error, we deal with that by chaining. And we also need a mixing scale type argument to deal with this one dependence. And so we have some successive conditioning to build up the right kind of filtration. And then we can get an empirical process theory going in this way. This is interesting in its own right. Xie Jiao, he used this idea because he was interested in IV problems, where we know that we have dependence between the regressors and the errors by construction, and then you can deal with that dependence using these kind of techniques he found. So that was an aside. So the point of all this is we use the consistency results to get this cutoff C, and the asymptotic normality, as I said before, it tells us two things. How does the sampling variation depend on these regressor types? And we have this numerical analysis in the paper. But second, one could think about constructing a test for outliers that Yao did together with Felix Pretis in the IIS situation where we had impulse indicators. You could perhaps do the same here, but we haven't thought about that. So further on the fixed C situation, then once you've done our algorithm, you would then go on and re-estimate beta. Unfortunately, we are not able to analyze that updated estimator. We can't do that at the moment. But we conjecture that there are some weird properties that we will also see in simulations. So basically, because you have a frequency case of gamma, then you expect to find n times gamma shifts by mistake. And since you have n observations, you divide by this number of periods, you get 1 over gamma is the average regime length. So if you think of a gamma that is 1%, then you would have about 100 observations in each regime on average. So we then conjecture that this situation is a little bit like the incidental parameter problem situation that we have in panel data. So we would think that if you have dynamic regressors, then you may get an asymptotic bias for the beta hat coming in here. And I'll show you some simulations in a moment. So that bias will be smaller the smaller you choose gamma. But if you then get into the business of choosing a small gamma, then you're essentially thinking about sequences of gamma going to 0. So we're then into the situation of these drifting situations where you choose gamma as lambda divided by n. And without estimation error, then we can think about the Poisson limit theorem. Unfortunately, you have the one dependence, so we can't use the standard result, but there is a very nice paper by Chen from 75 where he does exactly the thing we need. And then we need to deal with the estimation error. And in an earlier paper with Sonny Hansen, we found a technique that we can sort of modify to this situation. So combining these ideas, we get this Poisson result. And then our conjecture is that beta hat will be asymptotically unbiased in this situation. So this suggests that you should choose the gauge fairly slow, which I think is the general recommendation from David Hendry and Jennifer Castle and their co-authors. So let's have a few simulations of this situation. So we have a fixed C and updated beta estimation. I'll show you two types of simulations. In this situation, we have two GTPs. The first GTP on the left is where we have cross-sectional regression, if you like. We regress y on some x's that are IID normal, and the errors of the epsilon errors are also IID normal. And the true GTP has a beta equal to 0, but we try to estimate it by this procedure. So we first apply the stylized cis, and then we update, and then estimate beta hat again. And then you can see we have here the legend is over here. So if there's some red dots down here, and that is if we don't apply cis, just estimate the model, we get this kind of bias here. That's basically random noise. This scale is multiplied by 10 to the minus 3 here. If we apply cis with 10%, then we get the blue curves up here. So some bias, perhaps. With 5%, it's a bit less here, and with 1%, we're down here. So this is the situation where we don't have dynamic regressors. So we say get a quite good performance when the gauge is low and across different sample sizes. It's fairly stable. If we then go to GTP2, there we have an AR1. We choose alpha to be a half. We let the sample size increase. And we see we have this negative bias that we are used to in autoregressions. The red curve is what you would get without cis. The green is what you get if you have a 1% gauge, and with 5% gauge you're a bit off, and with 10% gauge you're even more off. So this shows that it works quite well, but we are systematically off the red a little bit. So let's look a bit further into this. And here we have looked further at this AR1 model, but we now vary alpha. So we're now varying alpha on this axis here. And so on the left, we have 10% gauge, on the right, 1% gauge. The red is what we get without cis, and the blue is what we get with cis. So you can see with a 10% gauge, we get a really big bias coming in that actually varies with the autoregressive coefficient. Then with 1%, we still have a bias, but it's a bit smaller. So there is some systematic bias coming in here in this situation. Okay, so the next thing I'll go into is talk about type 2 errors or power. So what I'll do is I'll look at some power properties of the stylized cis, and then I'll look at some power properties of the Andrews test. So let's start with the stylized cis. So we look at this situation where we have two sample halves. I've dropped the regressors because otherwise it gets too fiddly. So we just have a constant in the model. And so we saturate the second half with these step indicators. And cis will declare step shift if the t-statistics, which are now called Zi, which is delta yi, is divided by this standard error is bigger than c. So that's what cis does. And now we need to think about power. And so we'll think about two situations. We first think about power for a single step shift. We have a step shift of magnitude delta at time tau plus 1. And then what I will do here is I can look at all sorts of decisions, and I focus here at looking at the decision at time tau and the decision at time tau plus 2. It's because of the one dependence. If I move these two apart, then I can I get independence. So that makes my life a bit easier. And then because of this independence, I can then find out in a finite sample, I have a t-distribution. Asymptotically, I have this kind of probability coming out from the normal distribution. So we have a non-centrality here, delta divided by square root 2, and then we compare that to the critical values. And what we got out of this formula is that this is more or less constant in the sample size n for a fixed delta. So that means that you don't have consistency in the sense of the power going to 1. So this is a kind of a local power result. So this delta is the drifting sequence that is relevant here. So that's a bit disappointing, perhaps. But another thing we see is that this power is constant in location. We could choose tau in the middle, or we could choose at the endpoint, we get the same power. So that's very positive. Now, let's look at a situation with an up-down step shift. And we saw that was relevant in the data in our year 2000. We have some up and down thing happening, and a slightly different level after the up-down shift. So we have a magnitude delta shift at time tau plus 1. And then 2 periods later, we have a shift of nu minus delta down. So that what we should think about is delta is relatively large and nu is relatively small. So if nu is 0, you shift from one level, shift up and shift down to the same level. If nu is slightly different from 0, you shift from one level up and then down to a slightly different level, which is very important in our growth story or productivity story, that we shift from 0.5% to 0.4% or whatever it is. And so what we find out of this is that we again get a similar type of result. If we now look at, I guess it should be set tau, then we can show that that converges to this kind of result. And so what we get out of that is that we get a power to detect a very small nu as long as delta is large. So if you think of this delta as quite large relative to the standard error in the problem, then you have a lot of power coming from here. And so so that is a situation that can happen in practice, and we saw in the data. Now let's go to the Andrews test, and we'll try to do something similar. So for the Andrews test is about a one shift situation. So we have an overall level here, and we have a shift here of magnitude delta. And so what the Andrews test will do is for a given t, we test that delta is equal, given tau, sorry, we test delta is equal to 0 using a t-statistic. And then we say, well, tau is unknown. It's somewhere between a lower level and an upper level. And then we take maximum over all these t-statistics. And then it's custom to say, well, this n bar should be a proportion of n, and it's custom to take 15% off in the beginning and 15% off in the end. And then we can do asymptotic theory and find out that we get that the maximum of these t-statistics behave like a Brownian motion normalized. And it's because of that normalization, we can't go all the way out to the endpoint. And because we have a functional central limit theorem in here, we can tolerate epsilons that are non-normal. Okay, so let's think about power. So first, here's a slide about what happens if you have a single break. So suppose tau is equal to lambda times n. And so this lambda, I will allow it to be anywhere between 0 and 1. Although we only look at what happens with a test, we look at what happens between 15% and 85%, but I could have the tau outside, or the shift outside. Then I would say delta is now, it's a local power, so I can now allow myself to divide by square root n. So I have delta is phi divided by square root n. And then we can work out that the asymptotic power is of this form where you have a Brownian motion, you shift it by phi times this deterministic function. I guess I should have drawn it, but I haven't. So it's linear, you can see in U with one slope before lambda and another slope after lambda. And it will be largest for U, it's a continuous function, it's largest for U equal to lambda. And it takes this value here at where it's largest. So it's basically a function that increases from 0 up to this point and then down again. And so this gives us a kind of non-centrality of the test. So I can compare this thing with the critical values up here, basically. The cis non-centrality was delta divided by square root 2. Now, when I think about power here, I need to think about what happens with this, how this lambda is located relative to these cutoffs. So if we now take these cutoffs to be 15% and 85%, then we find if we choose a lambda, which is in the central part of the sample, then I can ask, when is my Andrews test better than the cis test? So cis is not consistent so it has a local power for a given delta, but for a given delta, Andrews test will be consistent. And then I can do some calculations, and they indicate that if you have less than 4 observations, then cis may actually be better than Andrews test. 5 if you have the break here, and 7 if you have the break here. But once you start getting a lambda that's outside the Andrews test region, then suddenly cis has some advantages. So if you get up to a break at 99%, then you need to go up to quite a large n before the Andrews test wins. So this is based on some theoretical calculations, so we'll simulate it in a moment. Now comes the exciting thing. What about the up-down situation? So now we have a DTP where we have 2 level shifts, delta 1 at time tau 1 and delta 2 at time tau 2. And we will investigate local power when tau 1 and tau 1 are quite close. And the up-down effect means that delta 1 plus delta 2 is very close to 0. And then I do I need to have some local experiment. So I say that delta 1, delta 2 is psi divided by square root n, so it's close to 0. Delta 2 times tau 2 minus tau 1, it's a weird combination that is psi times square root n. The tau 1 over n is going to lambda, and tau 2 minus tau 1 is going to something I can't see on my screen, but I can see here it's going to 0. And so we have these parameters coming in, and then we can find an asymptotic limit theory where we have the same S function as before plus a shift. And so that's the limit we get out of that. There's something very interesting about the proof of this, because we have this weird shift going on, then we cannot use the J1 metric from Skorohod that Billingsley calls the Skorohod metric. We have to go back to the original Skorohod paper, in which Skorohod actually suggested 5 different metrics, and we should use the metric, it's called the M1 metric, to be able to do this asymptotic. So that's sort of a minor thing that's quite fun. So read the Skorohod paper. It's a very important paper. Okay, There's also a book you can read by Witt from 2002, which is sort of a version of Billingsley focused on the M1 metric. Anyway, so we now have an example where tau2 is tau1 plus 2. We have an up-down shift here and this way. And then we can show in this situation, cis has a power that goes to 1 because this delta now goes to infinity, and Andrews test has local power. So basically, you can't say cis is better or worse than Andrews test. Some situations Andrews test is better, some situations cis is better. Okay, then we have some simulations here. I'll try to explain these. So our data tuning process is an autoregression where we have a step shift delta, and we want to see if we can find this. We apply either an Andrews test, I call that A, or we apply cis, a split half cis. And I think what we do is we look at the t statistics exactly at this point here. Then we can have delta, the shift of size 0, 2, 4, 8. So if delta is equal to 0, we're talking about gauge. And then we have different experiments here. One here where n is equal to 100 and alpha is equal to 0. One where n is a bit smaller, 66. That was a number we saw in this earlier slide. And we can either have alpha equal to 0 or some autocorrelation. Then we look at different lambdas that are outside the region that cis is Andrews test is interested in, but they're empirically relevant. So we have 90%, 95%, and 99%. And what we see is that the Andrews test has a size close to 1%, gauge cis has a size close to 1%, and that goes a little bit wrong when we have autocorrelation, but it's the right ballpark. Then we see here what happens with as we increase delta, then the Andrews test gets more and more power here in this line, and cis also gets more and more power, but slowly. One thing we then see is that for the Andrews test, the power depends a lot on the lambda. So if lambda is very extreme, it has basically no power. Whereas cis has a power that's constant. So if you have extreme situation, you would prefer cis. If you have a less extreme, you would prefer Andrews. And we see that again here for 66 observations. It's the same kind of business. So we over here delta is equal to 4, then you can see there's really a choice here between these. And if there's autocorrelation, cis actually doesn't change that much, but it seems like there's a bigger effect on Andrews test with autocorrelation in this simulation. Okay, so that's what we can say about this. One could also simulate more complicated situations, but this, we think there's an analogy here to more complicated situations. Okay, let's go back to the data and let's see if we can get more out of the data analysis now. And so we have the data here. You can see here 2004 was going to be picked up. You could say that from here and onwards, there's a linear trend, and here and onwards, there's a linear trend. So in a sense, Andrews test is right. From here, that's if you just want one break, maybe that's where you want to put it, but it's somehow not economically meaningful. And then we have the differences. This is the first regression we ran where Andrews points at this break in 2004. It's kind of meaningful, but economically we prefer the one in 2008. We then go on to where we saturate the second half with dummies, and then we get what we have here. And then we see that we have in 2000, we have some very big shifts. This is about 3 standard errors up, and then we go, I don't know, a bit more than 3 standard errors down. So we have precisely this situation where we have a big shift up and a big shift down, but overall we get a very minute change in the level. So that can be picked up here. We have the same thing happening in the financial crisis. And then we have sorry, this was in the end here, that's a COVID. And then we have the financial crisis here where something else is happening. And so what's happening here is that we actually don't have the situation where we have a big shift up and a big shift down. We have this sort of more gradual, prolonged crisis period where we first go down for a couple of periods and we go slowly up for a couple of periods and then we find a new level. And stylized cis is simply not good enough to pick that up. And so we had a little bit disappointing result here. I also tried to use CIS as it's implemented in Autometrics, in Oxmetrics software, and then you get a much more detailed outcome about you track the up and down situation much better. But with stylized CIS, it doesn't have power against this particular thing. It's too simple an algorithm we use. But the Autometrics algorithm has more choices, and then it seems it fares much better, and you get some more significant numbers throughout the financial crisis. Because what we do here is basically an average of a big change down in the economy and a slow change up, and we capture all that with one number. And so therefore it's going to be a bland, not so interesting number. And so we see here again, you can see very clearly in this blue line, you have a big shift up and a big shift down, a slightly changed level, which we can sort of see in the data that there's a slowdown after 2000. And then we have again a slowdown in 2008. The crisis itself is not modeled very well with this simple algorithm. And then we capture the COVID crisis. And as I said, Oxmetrics performs better than our algorithm. Okay, just to round off, then what we have here is we found this frequency gauge is consistent when we have stationary and non-stationary regressors, and we investigated the variability through this asymptotic theory and also some numerical analysis, which I didn't show you. There is we think there's a bias in the updated beta hat. We can't show that using our theory, but we can simulate it. You get that bias, we have a fixed cutoff, and so it's better to choose a drifting sequence, so a very small gauge. Of course, in a finite sample, you can't tell whether the C you choose come from a fixed C or from a drifting sequence, but one should probably think of it as a drifting sequence, and then probably use a Poisson theory. But we didn't get any further on this at the moment. In the power, we have this situation. If you have a single central shift, you would prefer the Andrews test. But if you have a messy real-life situation, as in the productivity data, then you have close offsetting shift, you have late shift, CIS is better. And on the regularity condition, CIS requires normal errors, but we can have non-stationary regressors, so you can actually apply this method without knowing too much about your regressors, whereas the Andrews test requires that you know that the regressors are stationary. And then there's some innovations in the proof techniques. We have this combination of using mixing-gale stuff from McLeish in the empirical process theory, together with the chaining. And for the Poisson theory, we use this Chen paper, which is quite nice. And then finally, there's the Scorrod paper about all these 5 different metrics that's useful for the power result. One question I have to the audience is, has anyone seen any power results for the Andrews test in this spirit? And that's it. Thank you very much.
Thank you very much, Ben, for the great talk and very clear one. So I'm gonna open, the discussion and questions from the audience, and possibly to start with our panelist, Jennifer Castle from Oxford.
Of course, great. First, thank you very much, Ben, for an absolutely excellent paper and presentation. It's really wonderful to see the asymptotic theory developed for CIS, which is a method that's